So in example 4b, we took the power series expansion of e to the minus x squared and we integrated it. We integrated it term by term. I don't know if any of you were like pausing when we did that and were wondering if that was legal. Were we allowed to do that? I mean, that is a mathematically valid question. And the answer is yes, you can do that as long as your function is well behaved. And so we have a theorem that allows us to do this and that summarizes what we can do. So this is the power series differentiation and integration theorem. So if we have a function f of x that has a power series expansion given right here, just our normal power series expansion, n goes from 0 to infinity, cn x to the n. So c0, c1x, c2x squared, and so on. If we know that that series converges absolutely for f of x on the interval of convergence, so x between minus r and r, then on that same interval of convergence, we have that we can take derivatives and that we can find antiderivatives, so that we can integrate. So f prime of x, we can find that by taking term by term derivatives of our power series. So when we take the derivative of c0, we get 0. When we take the derivative of c1x, we get c1. When we take the derivative of c2x squared, we get 2c2 times x. And then for the next term, we get 3c3x squared. And one more, for the next time, we'd get 4c4x cubed, and so on. So we really can differentiate term by term, and the derivative of f prime, is equal to the derivative, the term by term derivative of our power series. We can write down this in sigma notation, and we get n goes from 1 to infinity, n cn x to the n minus 1. We can also integrate term by term, and we already did that without really being allowed to, but we did it in the previous example. And so when you're integrating term by term, let me get rid of this so that we can look at it again. When we integrate term by term, when I'm integrating c0, I get c0x. And when I'm integrating c1x, I get c1 x squared divided by 2. And for the next term, I get c2 x cubed over 3. For the next one, I get c3 x to the 4th over 4, and so on. And then at some point I have a plus c, and since I don't want to tag it on after the dot dot dot, I'm actually going to write it up in front here. So this is our arbitrary constant that we always get when we find the most general antiderivative. And I can write this down in sigma notation as well. So we have n goes from 0 to infinity, and the pattern is we get cn, and then we have x to the n plus 1, just using the power rule for integration, over n plus 1. So whenever you have equality, a function is equal to a power series on an interval of convergence, then you can take the derivative and you can also integrate your function.